Before I introduce our speaker, I just want to give you some context for the evening. For me, one of the amazing things about astronomy is the way that in my lifetime we've taken fundamental philosophical questions that people have been arguing about for centuries and actually got answers. And so I want to illustrate what I mean by that with a couple of examples. What is the sun? And how does it shine? So earlier in the 20th century, Cecilia Payne, working in this building, discovered that the sun's atmosphere is made of hydrogen. And Arthur Eddington, working in the real Cambridge, found out that the sun and the stars were nuclear fusion reactors. And so now we understand where the sunlight comes from. A nuclear fusion reactor shining by the power of E equals mc squared. And so, that led to one of the other great discoveries. Where do the chemical elements come from? Why are some elements more common than others? There's lots and lots of carbon and oxygen and silicon in this room. Not so much gold and platinum, alas. And why is that? And so Fred Hoyle and others found out that, it's to do with nuclear reactions in the stars. It's nuclear fusion reaction rates that determine we make more of this element and less of that element. And so fundamental features of the world around us come directly from astrophysical considerations because of the poetic reason that you and I are truly made of stardust. And on a larger scale, Henrietta Leavitt, also working in this building, set one of the key steps on the distance scale to figure out how far are the stars. And by studying variable stars, she found out the distance to the Magellanic Clouds and gave us a tool that later led to the work by Edwin Hubble that gave us the first estimates not only of how big the universe is, but how old it is. And there's a question, right, that goes back thousands of years. Is, where did the universe come from? How old is it? And not only have we answered that question, right? We didn't just say, it's really old, right? Well, and then we got to, by the time I was in school, it's billions of years old. And in fact, it was either 10 or 20 billion years old, depending on who you believed. And then with the work by WMAP and other satellites and Hubble, we now know the answer is 13.7 plus or minus 0.1 billion years old. It's not often that you can take an ancient philosophical question and give a 1% numerical answer, right? So that's what's great about astronomy. Possibly one of the biggest and oldest questions in this category is what's called the plurality of worlds. Is Earth the only thing like itself in the universe? Is our solar system the only solar system? When I was a student, we didn't know whether there were other solar systems around other stars. We had no extrasolar planets, and so for all we knew, this was a freak. Now we know that isn't the case. Something that people have speculated about for centuries. We know that planets around other worlds are common. And we're only just starting to explore the implications of that. Now we have thousands of extrasolar planets now. We're going to get a lot more. We're just starting to probe them. So a new satellite has just gone up that is going to tell us a lot more. We're really lucky that our speaker tonight knows all about this satellite. So I'm going to tell you a little bit about Sam. Sam Quinn tells me that he grew up in Vermont, and he would go to astronomy open night at the local college in Bennington, was it?
Middlebury.
Middlebury, thank you, Middlebury. And so be careful. Going to open nights is dangerous. It can suck you in. And so after that, Sam came to Harvard and did an undergraduate degree. And he hung around for a few years working with Dave Latham here, studying extrasolar planets. And that was sufficiently interesting that he decided to commit. And he went to Georgia State University for a PhD and surveyed, did a survey for discovery of new planets. But also, you may not know, Georgia State is actually famous in astronomy for being really good at taking the sharpest optical pictures. It has the Char array, which is an optical interferometer, and so Sam was able to use that and other methods to sort of study the evolution of planetary systems and look at complex planetary systems. But the gravitational pull of Cambridge, Mass. was just too much. He could not escape the Harvard Event Horizon. So we dragged him. We dragged him back here, and he's now back with us as a PhD scientist, working on the TESS Observatory project and its connection to the world astronomical community. And so TESS went up. It's got its first data. I can't wait to find out. I don't know what Sam's going to tell us. So please, Sam Quinn, tell us all about TESS. Thank you.
Thank you, Jonathan, for the nice introduction, and thanks for everyone for coming. As Jonathan mentioned, I have kind of been here off and on for the last 15 years or so now, hanging around this building. So it's really nice to get the opportunity and the privilege to have the opportunity to speak at one of the open houses. I've always seen them occurring and thought it's a wonderful thing. So I'm glad to be able to share my research with you and some of the really exciting research that's going on in the field of exoplanets. So as was mentioned, I'll be talking about the TESS mission, the Transiting Exoplanet Survey Satellite. And TESS is a space mission that is headquartered out of MIT. It's a NASA mission run by MIT, and the science office is headquartered here at the Center for Astrophysics with another arm of it at MIT. So we work very closely up and down the river. I'm often heading downriver for 2 days a week to do some vetting and try and discover new planets coming out of TESS, back here to do some analysis and organization. So I also just want to point out, so this image here that I've shown on the title slide is the K2-138 system. This was the first planetary system discovered by citizen scientists. So there's a whole range of activities that are occurring around the field of exoplanets, not just with scientists, but with amateurs, with enthusiasts who can actually dig into the data and make real discoveries like this. So I encourage all of you who are excited to get their hands on actual data to seek this out. So before I dig into the actual meat of the talk, I want to give you a crash course in the history of exoplanets, how we find them, and talk about where we're headed as a field and how TESS will contribute to that. So I want to cover what we know about planets, how likely it is that they form, how are we going to understand the planets that we know about, how do we understand the formation and the evolution of those planetary systems, why do we care, how likely is it that there are Earth-like planets out there, when we can start to address these really great philosophical questions that have been around for centuries. Are we alone? How likely is it that there's life in the universe outside of Earth? And then, of course, what is TESS and why do we need it? And those are sort of, those first couple bullet points are leading you to the answer to that question. And what will TESS find? How will we study the planets that TESS finds? And what do we hope to learn from them? And then now that TESS is launched and we're starting to get data, I will spend the last few minutes of the talk showing you some of the results that have come out of the first month of TESS data, and hopefully convince you that TESS is starting to deliver on its promise to find small planets around nearby stars. So first, many of you are probably familiar with some of the basics of exoplanet science, but many of you may not be. And so I want to talk about how we discover exoplanets. So there are a couple main methods that people have used up until now to discover planets. And the first is the radial velocity method, or the wobble method. So as a planet orbits around its star, the star also orbits around the planet, or rather they orbit the center of mass together. So you can see that the star is wobbling back and forth, and as it wobbles back and forth, the star's spectrum, the light from the star, also shifts back and forth. This is the Doppler shift, and by measuring the positions of the lines in the atmospheres of stars, we heard that the atmospheres of stars have hydrogen. They also have helium, and they have smaller amounts of other elements. And so those elements absorb at specific wavelengths, and when we watch the spectrum shift back and forth, we can deduce that there is an unseen companion tugging on the star. And if you make those measurements over time, and you measure the velocity, the radial velocity, we measure the amount of the motion that's in our line of sight moving towards us and away from us. You can build up measurements over time and observe an orbit. And from simple parameters of that orbit, those measurements, you can figure out what is the amplitude and what is the orbital period. So how long does it take to repeat one time? And it comes back around and does it again and again. So the time to complete the orbit gives us the period, and then the amplitude is related to the mass of the companion. And so it's some basic physics gets you the mass of the companion, or at least the minimum mass. We don't know the orientation of the orbit. It could be moving really fast in the plane of the sky, and only a little bit of it is coming towards us and away from us, which is what we measure. So we measure a minimum mass. There are, of course, lots of challenges to making these measurements. So this video on the right here is the sun. So people often think of stars as these kind of everlasting, constant balls of light. They're not constant. They're not constant at all. They're actually really dynamic. These are convection cells on the sun. You can see them slowly moving. And these are really large. So the scale of these, I think, is hundreds or 1,000 kilometers or something like that. And so these induce all sorts of problems. There are many things that inhibit us from finding planets. Some of them are things that we can control or correct for, problems with our instruments, the Earth's atmosphere, other planets in our solar system tugging on the sun and the Earth and making it seem like we're moving towards the star instead of a planet causing the star to move toward us. We can correct for those things. But other stars may have other planets orbiting them, so there may be complicated signals, and more than one planet tugging on the star will cause all sorts of complicated wobbles that you can't model very easily. Certain stars are more amenable to measurement, so we can select for those. But then every star has some of this jitter, this excess motion. So whether it's convection or some stars, this again is the sun. Some stars have flaring. You have outbursts from the stars that can really affect your measurements. And I'm going to let this play for a moment because it's really just a really stunning video. And the sun is known as a quiet star. You can see this loop forming on the surface. The sun has magnetic fields, and material follows the magnetic field lines. And as the magnetic field protrusion comes out farther, you can see it get larger. And it'll show you the Earth for scale in a moment here. There's the size of the Earth relative to the sun. So these are enormous features. And the sun, again, is a quiet star. There are stars much, much more active than the sun with all sorts of phenomena like this happening all the time. So all these things can really make it hard to determine whether or not there's a planet there. Some of these things can mimic planetary signals. So in the midst of all of these things, we're trying to, if you want to find an Earth-mass planet orbiting a sun-like star in a 1-year orbital period, the wobble of the star that you need to detect is something like 9 centimeters per second. And this is really, really slow. In fact, it's about the same speed as a tortoise. So it would narrowly beat a tortoise in a foot race. And of course, if it can beat a tortoise, it can beat a hare. But no, that's another story. But again, the radial velocities only give us the minimum mass. So you go through all that trouble and you measure a tentative signal and you think, okay, well, I think I have an Earth-sized planet, but maybe it's actually just really inclined and it's much more massive. So what's the solution? Well, we need some way to determine the inclination of the orbit so that we know we're measuring the full motion of the star. So how do you find edge-on planets? You look for them passing in front of their stars. So this is the other major method of planet discovery that has been really effective in the last decade and a half or so. I guess it's been almost 2 decades since the first transiting planet. But it's really been the last decade or so that it's really come into its own. So when you have a planet passing in front of the star in our line of sight, it blocks out some small fraction of the light coming toward us. So if you measure over time the brightness of the star and you see a dip, and then you see it repeat once every, say, 3 days or 10 days or once a year, then you know the orbital period is 3 days or 10 days or a year. And the depth of the dip corresponds directly to the size of the planet relative to the size of the star. So it's the area blocked. So if you see a 10% dip, then it means 10% of the star is being blocked. So if you know the size of the star, you can figure out the size of the planet. And it's just a simple area ratio, the radius of the planet divided by the radius of the star squared. There are also challenges for transit surveys. Every time you see a dip, it doesn't mean that there's a planet there. Sometimes it's another star. So it could be a planet. It could be, turns out actually Jupiter mass planets are about the same size as brown dwarfs and small stars. So one Jupiter radius could correspond to something that's about the mass of Saturn all the way up to something that's 100 times Jupiter's mass. That is a star of its own that fuses hydrogen into helium. So you have to then make follow-up observations. It's the combination of the transit and the wobble that gives you the mass and the radius. You can also be fooled if you have, how do you make a shallow dip that looks like an Earth-sized planet? It could be a real Earth-sized planet, or it could be a bright star with a fainter star nearby that has a deep eclipse. So if you have an eclipsing binary system, 2 stars, and it creates a deep eclipse on this star, when it gets diluted by the light from the brighter star, it'll look really shallow, like an Earth-sized object. So these are all, and you can have kind of different geometries that only block a small fraction of the star that can also look like shallow eclipses. So it requires careful investigation of the data themselves, but also follow-up observations to determine what we're actually looking at. Okay, so you guys are ready to find planets and characterize them now. So let's go ahead and talk about what we've found. So the very first planets that were discovered around other stars are interesting. I mean, it's a sample of a few, and they're really interesting in their own right. The first, it comes with a little asterisk for now, was discovered by Dave Latham, who works here and has been here for many decades now. He and Robert Stefanik and others worked on this system. In 1989, they published a paper. They called it a probable brown dwarf. So brown dwarf is like between planets and stars, failed stars, some people call them. So they're interesting too. And the reason they did that is because there were no known planets outside of our solar system. They were being cautious. And this particular planet was at an 84-day orbital period. And it was the size of Jupiter. It's actually much bigger than Jupiter. It's 10 or 11 times the mass of Jupiter. And so they were puzzled. They thought, how do you form a giant planet that close to its star? That's about the distance. That's about the orbit of Mercury. We don't understand. It went against our understanding of planet formation. And so they hedged their bets and said a probable brown dwarf. Well, a few years later, there were some small planets discovered around pulsars, dead stars, stars that had exited the main sequence, the prime of their life. They'd shed their outer layers. In fact, these were probably remnants of the supernova. And then tugging on these pulsars, they determined that the timing was off, and they determined that there were planets tugging back and forth on the timing of the pulses you get from the pulsars. So those are both really weird systems. And then the third one that is often recognized as the first planet around main sequence stars, around the star 51 Peg, was a giant planet, again, Jupiter mass, in a 4-day orbit. So once 4 days is its year. So on that planet, it takes 4 days to go around the star. That's crazy. That's unlike anything we'd seen. We knew binary stars could do that, but how do you form a planet there? So these hot Jupiters and kind of warm Jupiters and planets around dead stars, we're already seeing from the first few discoveries that there's an incredible diversity of planets in the universe. So since these don't look like our solar system, you have to think, oh, maybe our solar system's weird too. Maybe it's, a one-off, like Jonathan was saying at the beginning. Maybe, even though there are planets around other stars, maybe habitable planets aren't that common. So we want to know how common are planets and then how common are habitable planets. So the title slide said that I would also give an homage to Kepler. And the reason is that very recently Kepler, which was NASA's first planet hunting satellite, ran out of its fuel after a good run, 9-year run, and it contributed an incredible amount of knowledge to the field of exoplanets, our understanding of how planets form, how likely it is that planets form, and has given us just a wealth of information, not just in exoplanet science, but in stellar astrophysics and other fields as well. So Kepler was a mission that stared at one patch of sky uninterrupted for 3.5 years, looking for transiting planets, to find small planets and determine how likely it is they're small planets, specifically in the habitable zones of their stars. It failed after 3.5 years and was actually resurrected as the K2 mission, which I'll talk about later, and recently has finally gone silent as its fuel ran out. So I want to talk about I talked about this idea that exoplanets are a diverse population. So I think what I want to do is show you some of the highlights, some of the really weird systems, like the fun ones to think about, before coming back to kind of what Kepler has taught us about the population as a whole. Because I think you learn really interesting things both from the extreme cases, but also by studying populations. And that's also something that I think TESS will be able to do really well. So this first one is not a Kepler discovery. This is discovered by the KELT survey, the Kilodegree Extremely Little Telescope. Astronomers love their acronyms. This is KELT 9. It's a hot Jupiter, like we talked about. The orbital period is 1.5 days. It whips around its star every 1.5 days. So this is incredibly close to the star. It's massive. It's bigger than Jupiter, 2.5 times the mass of Jupiter. And it orbits a star that's greater than 10,000 degrees. So the Earth is 5,800 degrees Kelvin, and this is an A star, maybe even no, it's not a B star, it's an A star. And so the planet itself is absolutely scorched on the day side of the planet. The planet is 4,600 Kelvin. That is hotter than most stars. Let's just let that sink in. This is a planet that's hotter than most stars. People try to model the atmosphere, and actually they have to build special code. Nobody's code models planetary atmospheres that hot. It's caused problems for folks. So the best way to do it, I think, is to model it as it's two stars, and you have heating from the other star in the atmosphere of the planet. So it's a really interesting system. Again, this is one extreme case. You can study the atmosphere really well because it's hot. It's a large planet. It covers a lot of the star. The star is bright. So you learn a lot of things about the composition of planets when you have extreme cases like this that are easy to study. Another one that I really like is Kepler 36. So this is a Kepler discovery. I like it for a couple reasons. One is that it's a multi-planet system. There are 2 planets in the system. And that's actually a common state for planetary systems. Small planets tend to be, are often found in multiple planet systems. But this is also dynamically really interesting. They're really tightly packed together. The orbital period of the interior one is 14 days, and the exterior one is 16 days. So they're right next to each other. Then they're in a 6 to 7 resonance. So for every 7 orbits of the inner one, the outer one does 6 orbits. And then they come back to the same spot and line up. And because they spend so much time coming back to the same spot, and they interact gravitationally, and they tug on each other and give each other kicks in their orbits. So this plot here, this little waterfall or river plot, is showing the transit time as a function of transit numbers. So if they were not interacting, like most planets, and they just went around like clockwork every time, you would have a straight blue line. Let's focus on this one because it's a deeper transit, so it shows up as higher signal to noise. You would have a straight blue line right up the middle. But you don't. We have this meandering and anti-meandering curve here. And if you look really closely, after 6 orbits of the outer one, it does a big jump. And then another 6 orbits, and it does another big jump. And if you count, it would be 7 orbits and a big jump. And that's because that's where they line up really closely, and they kick each other. And from that, you can get really precise masses of them. So you don't even have to do the wobble method. You can actually figure out from the interactions between the planets how massive each of them is. And the interesting thing you find is that they have really different densities. They're about the same radius, I believe, but the densities are really different. So one of them is denser than the Earth, and the other one is less dense than water. So how do you get that two planets that form right next to each other? Maybe they didn't. Maybe they formed far away and came closer, that have really different compositions. And then it's also fun to think about because if you imagine, so these are not habitable planets. They're too close to their star to be habitable. But if you imagined that planet B were habitable and had a city like Seattle, for example, and you peered up at the skyline at planet C, it would look like this. So like these are just extreme cases of planetary systems that you can learn a lot from studying, right? This is a real puzzle, and people are interested in how planets form, how you build planets in different parts of the disk around the star. So by studying systems like this, we can gain insight into that. Okay, so sometimes it's not just one star that hosts a planet. Sometimes you have two stars that host a planet. And so this is Kepler 16, which is the first circumbinary planet that was ever discovered. The planet transits both stars, and the stars both eclipse one another. So the binary, you have two stars in a period of 41 days. So they eclipse each other once every 41 days. And the planet, exterior to that, going around every 229 days. And this is like a Saturn-sized thing. But because they all eclipse each other, again, you can get masses of the planet and the stars really precisely just from the timing of these measurements, of when they tug on each other just enough to then you measure the transit time or the eclipse time, and you can back out what the physical interactions are, how massive they have to be to do that. So there's a nice little movie here. So you'll see a big dip here as the little star goes in front of the big star. Then here comes the planet, and there's going to be a little dip as it goes in front of the big star. And then it's going to come over in front of the little star. So you have to really squint to see that there's the dip right there. And then this one goes behind the big star. And this will continue for a while. But so those little events, the precise timing of those events, tell you about the masses of the objects. So we've got multi-planet systems, hot stars, giant planets, circumbinary planets, tiny planets too, disintegrating planets. So this is an example of a system that's a white dwarf star. So again, a dead star. And there's something causing a huge dip. This is 40%. It's blocking 40% of the light. Now, white dwarfs are really small, so it's easy to block a large fraction of them. But at the same time, that's really extreme. And it's a weird shape. I showed you in the beginning, it was kind of, you'd expect it to be symmetrical. But this is a weird tail. And we can model this to show that it's actually a disintegrating planet. Really, not really even a planet. It's just kind of like a little asteroid. You can see the size of this thing, 100th the size of the Earth, and smaller than 1,000th the mass of the Earth. So this is like a big asteroid that we can detect because it's around a tiny star and because it's outgassing and ejecting debris. So the big cloud is what's causing that deep eclipse. Now, one of the more exciting systems that's been in the news in the past couple of years is the TRAPPIST-1 system. So most people in the field are really excited to find small planets. We're really excited about habitability. How likely is it that there are worlds that can support life? And this is a really exciting system for a few reasons. One, it's around a really, really cool star. So it's telling us when we survey stars that are unlike the sun, it tells us about kind of the range of outcomes of planetary formation. So we know about our solar system. Most of the stars that people have surveyed with radio velocities, at least up until this point, up until when Kepler was launched about a decade ago, were kind of sun-like stars. They were the brightest and easiest to observe for a few technical reasons. But small stars like this one are among the most common. They are the most common type of star in the universe. Most stars are much smaller than the sun. And so it's really interesting to learn about what planets are like around those stars. They're also really long-lived. So if you have a civilization that evolves around one of these stars, it could potentially advance much farther than a civilization around a hotter star where the star dies after a couple billion years. So understanding these outcomes is really exciting. And this particular system has 7 planets, all detected in transit, and they're all about the size of the Earth. The star is incredibly cool. It's only 2,500 Kelvin, so it's among the very smallest stars. You can see the mass of the star is only less than 1/10 of the mass of the sun. We think the smallest star that can fuse hydrogen into helium is just smaller than that, maybe 8% or 7% the mass of the sun. And what's more exciting is that 3 of these may be in the habitable zone of their star. So the distance at which liquid water could exist on the planet. So it's the right temperature. It's not too hot, it's not too cold. And so the orbital periods are very short, between 1.5 and 25 days, yet a few of them could be in the habitable zone, and that's because the star is so cool. So it's not putting out a lot of energy, so the flux hitting the planets is much smaller than it would be around the sun at those distances, and so they end up being roughly the right temperature to support liquid water. There are other questions about habitability of small planets. M dwarfs tend to be really active when they're young, so they have a lot of high energy radiation that could potentially strip atmospheres from planets. So you'd be relying on outgassing of secondary atmospheres, which actually happened here on Earth as well. So it's not out of the question, but people are a little skeptical. Some people are skeptical about whether or not you could have habitable planets around M dwarfs. But the fact is that there are so many M dwarfs, and I'll tip my hand a little bit here and say so many planets around M dwarfs. I'll show you that later. That it's really exciting to think about. So this is the transits of each of the successive planets, and here's a little top-down diagram, the star in the middle. And you can't see it very well here, but there's kind of well, I guess the dotted lines are probably the habitable zone rather than the gray region. So the dotted lines are the conservative estimate of the habitable zone, which includes 3 of the planets. So they all may be the right temperature to have liquid water, which is really exciting. It's not too far away either. It's something like 30 light years away, which is, it's going to take a long time to get there. But in astronomical terms, it's not that far away. So what have we learned from all this? Their planets are really diverse. There are all sorts of different types of planets around different types of stars. It seems like everywhere we look, we're finding planets. There's any planetary system you can think of seems to be created by nature. And that's exciting. That tells you something about how likely it is that planets form. If they're forming in all these weird places, they must also form in the normal, boring places. So I'll skip to the answer and show you this little animation of the history of exoplanet detection. So we have mass of the planet and the orbital period. So the Earth would be right there. So the blue ones are the solar system planets, 1 year and 1 Earth mass. Now these are the RV planets, radio velocity planets, came in around in the 90s and early 2000s. And then you start to get transiting planets in red. And then Kepler came along and starts finding these small planets in short periods, right? So it takes a long time. You have to observe a transit once a year to find an Earth. So Kepler observed for 3.5 years, so it only barely started to get into the true Earth analogs. But just the sheer number of planets that have been discovered, you can see the count over here in orange, and it reaches up to the thousands by the time this little animation ended, which was a couple of years ago, I think. There are also other detection methods, so you can directly image some large and distant planets that are far away from their stars. There's microlensing. Hopefully soon there will be astrometry. So lots of ways to find planets. I also like, so there's Pluto there. Keep an eye on it. Where is it? Oh, sorry, it's gone. No, it's still there. It's still there, and it's still a dwarf planet. It's still there. Nothing's changed. You might also notice down in here, keep an eye in here, 1810, something appeared. Oh, it went away. So Pluto wasn't the first one to be demoted, right? That was Ceres. That was the largest asteroid in the main belt. And it was considered a planet for a couple decades in the 1800s. And then when they started finding all those other asteroids, pesky asteroids in the main belt, I thought, we can't have 30 planets in the textbooks. Let's get rid of them all. So Pluto is in good company and still there. Still loved. So another way to visualize all these planet discoveries. These are animations by Hugh Osborne, by the way, and he's placed all of the known planets at the time of the creation of this around a single star, and there's a scale here. So this is 0.4 of an AU. So an astronomical unit is the distance between the Earth and the Sun. So these are really close to their stars, like you saw in the red points that filled up that diagram before. They tend to, looks like they're in mostly circular orbits, but then you see some that come in these weird elliptical, eccentric orbits. And it's just astonishing. Now we're at 0.2 of an AU. That's still inside Mercury's orbit. These are all the ones that we've discovered thus far. And it doesn't mean that they're not common farther away. It just means that we're really good at finding the ones that are close. It's more likely to transit. They exert a larger wobble on their stars when we're measuring the velocities. But as you get farther away, so now here's the Earth. So there's Mercury, Venus, Earth. Just the sheer number of planets that we've discovered around other stars is incredible. And we expect that, there are also planets out here. They're just harder to find. And we find some of the larger ones. These are mostly planets, Jupiter-sized planets that have been detected by the wobble of their star. It's just really unlikely that they transit so far away. So I think it's just like a stunning visualization to see, this is what we've explored. We expect there to be similar numbers far away. So what do we learn about how common planets are then? I've shown you some images. I've shown you some interesting systems. One of the really exciting things to come from Kepler, probably the most exciting to me, more exciting than the individual discoveries, is this one graph. Really, it's this one graph and others like it. There's a second one that I'll show you that I'm also very excited about. But this was done, so a lot of this work that I'm showing was done here at the Center for Astrophysics this was Francois Frassen, who is no longer in the field, sadly, but did some really nice work on the Kepler data, showing that for short period planets, again, the ones interior to Mercury, because those are the ones that Kepler was most sensitive to, most stars host planets. 52% of, and this is like kind of sun-like stars, host at least one planet. So the total number of average planets per star is larger than that, about one planet per star for sun-like stars at short orbital periods. And the other exciting thing about this plot is you have the radius of the planet here on the x-axis, and then kind of like the likelihood that you have a planet of that size on the y-axis, planets per star in this orbital period range. And so you can see, so Jupiter is out here at 11 Earth radii, and Saturn is like 8 or so, and Neptune and Uranus around 4, and the Earth and Venus and Mars and Mercury are down here. So in our solar system, we don't have any of these planets, but these are the most common type of planet. So this is exciting for a few reasons. One, small planets are common. That's the most exciting thing. Small planets are common, and there's also this intriguing population that we don't have in our solar system. They're short period, and they're between the size of the Earth and Neptune. So what's going on? What does that mean from a planet formation standpoint? What implications does that have for forming Earth-like planets, for forming planets that are habitable? Are these habitable? Are they more like Neptune or more like the Earth? You can look at this another way, looking just at M dwarfs. This was by Courtney Dressing and Dave Charbonneau. Courtney is now a professor at UC Berkeley. Dave Charbonneau is an illustrious professor here. And so maybe the plots are a little busy, but the takeaway here is similar. This is the radius of the planet and the planets per star. So small planets are much more common than large planets. And this is the total number of planets per star in each period range. This is one planet per star at these period ranges for small planets. So for small stars. So for M dwarf stars, for small stars with relatively short orbital periods and small planets, there are 2.5 planets per M dwarf. Let me say that again. There are 2.5 planets per M dwarf, and there are 100 billion M dwarfs in the galaxy. That's incredibly exciting. Maybe you're not as excited as I am. I'm really excited by that. And so if you kind of break this down by separation from the star, there's one habitable zone small planet per star, per M dwarf. So one small habitable zone small planet per M dwarf. And you can kind of work the numbers and say probably the nearest habitable zone small planet is only a couple parsecs away, so only a few light years away, 6 light years or so. Actually, it turns out that our nearest neighbor has a small planet in its star's habitable zone. Proxima Centauri has, now we don't know its radius, we don't know its true mass because it was discovered via the wobble, but a small minimum mass of, I don't remember now, but it's a couple Earth masses, a few Earth masses. So it's likely to be rocky, and it's in the habitable zone of our nearest neighbor. So closer than that. And probabilistically, the nearest transiting planet like that is only 8 or 9 parsecs away. So this is again really exciting. In the last couple of days, you may have seen news that Barnard's star, which is actually the closest single star to us, and the second closest star system, also has a small planet orbiting it, a rocky planet, likely rocky planet. So these planets are everywhere. These types of stars are everywhere. Even for sun-like stars, planets are everywhere. So now we have to dig in and find out which ones are habitable, which ones are likely to be habitable. So I'd shown you a similar graph before, the one I was really excited about, and kind of plateaued. Well, it turns out that when that first graph was made, we didn't understand the properties of the stars all that well. So this was work done by B.J. Fulton and a team in California, where they basically went back and studied the stars that hosted the planets and said, okay, maybe if we can figure out what the stars are. So remember, when you get a transit, you measure the ratio between the size of the planet and the size of the star. And you measure the ratio between the mass of the planet and the mass of the star. So if you don't know your stellar properties well, you don't know your planetary properties well. So they went back and measured really precisely what the stellar properties were, and they found that this was not a plateau, it's actually two peaks. So there's a really common type of planet that's like around the size of the Earth. There's also one, this size that we don't have in our solar system, that's a couple times the size of the Earth. And so are those also rocky and potentially habitable? Or are they more like Neptune? Or are they some other class of planet that we don't know about? Maybe they're water worlds. I don't mean made completely of water, but that have a lot of high mean molecular weight material in their atmospheres. Maybe a lot of water in their atmospheres and on the surface. It could be other things as well. So maybe those are not likely to be rocky because you'd think that if they were formed the same way that nature would like a smooth process and you'd have a single peak. Maybe this is an earlier state of those and you undergo photoevaporation. If they get too hot, they lose atmosphere and become smaller planets that are rocky cores. So there's a lot of active research in this area. And one way you can distinguish between the two populations is by measuring the mass. So we talked about how the techniques are complementary. You get the transit, so you get the size of the planet, and then you measure the wobble, and you get the mass of the planet. And so it's really hard to do for small planets. If you want to measure the wobble of the sun with the Earth going around it, our instruments are such that you're looking for a shift in about, the amplitude of the shift is something like 1/10,000th of a pixel on your camera. And so you have to be able to reliably make that detection to measure the mass of the Earth going around the sun. So it's hard to do, but there are a handful of small planets that have well-measured masses. There are a lot more small planets that we know of, but most of them don't have well-measured masses. So you have mass and the radius, and these lines are lines of constant composition. So you see Venus and the Earth lying along this line. So these have similar densities to the Venus and the Earth. I won't say that they're Earth-like or that they have water, but they have similar densities. So they're terrestrial planets. But if you get above about 2 Earth radii, they start to go up onto this 100% water line. It doesn't mean they're 100% water. It probably means that they're a rocky core and then a lot of hydrogen and helium on top of it. But by filling in this diagram, by measuring the masses, we can learn about the compositions of planets, how they form, which ones are likely to be habitable. So with that, I think is a good time to transition. I'm going to say a brief word on K2, Kepler. Oh, so I was going to transition to TESS because TESS is promising to fill in this diagram, basically. TESS is going to find the small planets around the nearest bright stars, ones where it's easy to make those measurements. You have a lot of light, your signal to noise is high, and so you can measure masses for small planets, for things under 4 Earth radii, so really fill in this diagram. And so that's one thing that we're really excited about with TESS. But in between Kepler and TESS, there was this interesting time where, so Kepler was pointing at one field, and it was able to do that because it has reaction wheels that keep the spacecraft pointed in the right direction. They spin to impart momentum to the spacecraft and have really fine pointing. Well, the second of its 4 reaction wheels failed after 3.5 years. And so you need 3 to point on 3 axes precisely. And so people thought, okay, the mission's dead, it can no longer point. But some really clever people at NASA and Ball Aerospace figured out that you can actually point it, if you're always pointing it away from the sun, then the solar radiation pressure can kind of balance against the solar panels and point you in the 3rd direction. And every once in a while you drift too far and you have to fire a thruster to get back, but it worked pretty well. And along with some clever analysis techniques, the data were almost as good as the primary Kepler mission. We couldn't point at the same field anymore, So instead, you had to always follow along the ecliptic, the path directly pointing away from the sun in the orbital plane of the spacecraft, which is also the orbital plane of the planet, it's the ecliptic. And so you get, every now and then, you have to march along the ecliptic and observe a new field. And so K2 was kind of like a nice intermediate step for TESS because it's observing a larger portion of the sky, like TESS is going to do. TESS is an all-sky mission. And finding brighter stars and kind of seeing what we can do in these other fields. One of my favorite descriptions of Kepler, of K2, though, came from Dan Fabrici at the University of Chicago, who referred to it as zombie Kepler. So zombie Kepler lived on for about 4 years, and then even zombie Kepler died recently. But this is like a little cartoon that folks at NASA put out showing one of the fields that K2 was observing. You know, there's solar system objects that whip through because it's observing in the ecliptic. You observe planets, you observe young clusters of stars, even extragalactic things, supernova, accreting black holes, flare stars, all sorts of stuff. So K2 also did a nice job of kind of paving the way for TESS and showing what sort of other astrophysical phenomena we'd expect to observe. So with that, I'm going to now jump to TESS and devote the rest of the talk to TESS. I've talked about it a lot, but haven't really given it a good introduction. So TESS is an all-sky survey, and I've said a few times it's going to find planets around the nearest, brightest stars, and that's because it's going to observe all of them. So it was launched in April and began observing in its science mode in July, late July. And so the two things that TESS, that I think TESS will really do, actually it'll do many more, but for planets, the two things that it should do are find the best examples that can be studied in great detail of planetary systems. So around bright stars nearby, things that can be maybe imaged one day, things that many, well, if you talk to some folks, even some folks in this building, it may not be many years before we can send probes to them. There are initiatives ongoing to explore the feasibility of that. Breakthrough Starshot is the name of that. But anyway, these are the systems, our nearest neighbors that we'll be studying for decades to come because they're so bright, and once we find interesting planets around them, those will be the objects of our study. At the same time, if TESS can observe a large number of systems that can then be have their masses measured, you can build up a large population to really understand the compositions of planets, which is something that Kepler has hinted at, but TESS will really take that torch and run with it. I also think it'll be really cool because it'll find, if you survey the whole sky, you're going to find all sorts of weird things. So all those weird planetary systems that I showed at the beginning, I expect we'll find a lot more very strange things with TESS. So TESS is actually not that big. Kepler's mirror was almost a meter in diameter, and TESS has four cameras and 4 lenses, and the lenses are only about 10 centimeters. So it's a modest-sized telescope, and you can see people working on it in the clean room before it launched. And so even tiny telescopes can contribute immensely to this field, especially when they're in space, and come with really nice detectors and a well-run mission people with experience. So it's nice to be a part of this. But what I want to show is kind of the observing strategy of TESS before I show some of what we expect to find and what we have found so far. So like I said, TESS has 4 cameras. This is the international sign for TESS, by the way. You'll see why in a second. So they point in a strip along, so going from the ecliptic plane up to the ecliptic pole. And so the 4 cameras each has a field of view of 24 degrees on a side. And so they cover a strip of 24 by 96 degrees. So they reach all the way from the ecliptic plane up to the camera 4 is centered on the ecliptic pole. And the reason why will become clear in a second. So it'll observe for 27 days, which is 1 lunar month, 27.4 days. And that's because it's in an orbit that's in a 2-to-1 resonant orbit with the moon. So for every orbit of the moon, TESS makes 2 orbits. And it does this for, well, stability reasons. Apparently it's stable for decades to come, and it actually has enough fuel to operate for decades, supposedly. Part of that is because the launch went so well. And so every 27.5 days, it'll change fields and step around, and then after 1 year, it'll go and observe the northern hemisphere. So right now, we're in our southern hemisphere survey. And the interesting thing is that there are these overlap regions near the poles. And so those regions get a full year of observation. So you can find smaller planets and longer period planets. And those are, the locations of those are important because those are also the JWST continuous viewing zone. So James Webb is this next generation Hubble Space Telescope that's going to cover into the infrared as well, assuming it launches. I really hope it does. It's set now to launch in 2021, I believe. So people are really excited about that. And the nice thing is that TESS will find the planets that JWST can observe really easily in these regions, in the southern and northern ecliptic poles. And finally, one more video just to show you the contrast between Kepler and TESS. So this is the Kepler field, the original Kepler field. There's one TESS camera, and it'll zoom out and show the other three TESS cameras. And now it's going to unravel the celestial sphere and project it and show you as TESS. So those are the K2 fields along the ecliptic. And this also shows really nicely that they're very complementary in terms of sky coverage. So K2 did a nice job of covering the ecliptic, and TESS will cover everything else, up to about 85% of the sky, because the ecliptic's not covered and you have these little gaps here and there. So it's a really exciting time to be in the field of exoplanets because we expect tons and tons of discoveries. So I said TESS has launched and started taking data. So here's the TESS first light image showing the strip of cameras. So this is at the southern ecliptic pole right now, right there. And this is up near the ecliptic plane. And blown up into each quadrant is each camera. Each camera has four quadrants of its own, different chips. And you mentioned, you will notice some large features that are recognizable. This is the Large Magellanic Cloud. This is over here. This is the Small Magellanic Cloud. So just the scale of the field of view is incredible, and you see stars strewn throughout. You can zoom in and see a closer view of the Large Magellanic Cloud, and just millions and millions of stars. You can label some of these things for people who are interested. Some known bright objects. You could spend hours looking at these images. Now, I think this only works if I hit the play button. So during commissioning, there was a span of about 17 hours when the spacecraft kind of stared at one spot, similar to the way it would normally. And it happened to be observing a field where a comet was discovered. So this video, I think it'll start playing in a second, will show you the comet moving across. I don't remember the pace at which they point things out, so I'll probably point things out at the wrong times. But there's a little tail to the comet you can see, and you can see it actually changing direction. First it's heading this way, then it's heading that way. You can see stars blinking on and off. So what's happened in the processing here is this is a difference image. It kind of like takes the median of all of them, and then for every frame shows the difference between the median image and that frame. So things that are changing in brightness or position will appear to blink on and off or move, and the things that kind of look like messy holes with lights coming through them are just stars that are processed a little weird. So variable stars. There's this wisp of light that comes through. It's hard to see from this angle. Comes through here. It goes along this way. That's reflection from Mars, internal reflection of the detector when Mars went by on some other detector. And then there are asteroids all over. So the things that are moving very slowly, you can see them move back and forth as you move back and forth. And they're all over the place. So this is one 17-hour segment of one tiny little portion of one of the TESS detectors in commissioning data, so it's much better now. And all of those things popped right out at you with minimal processing. A comet, variable stars, asteroids, more than I could count in that amount of time. I think somebody went through and counted, and there were many dozens of asteroids just in that one little tiny portion of the detector. And TESS isn't even observing the ecliptic where most of the asteroids are. It's avoiding it. And so you can learn all sorts of things that are not planets. But what I care about are the planets. And so this was a simulation done before TESS launched by Peter Sullivan at MIT how many planets we expect to find given TESS's observing strategy and what we know about the occurrence rate of planets. And so for the really small things, TESS won't do a great job of finding the very smallest things, but these will be around the brightest stars. So you only need a handful of these for it to be really impactful. So an expectation of about 70 things smaller than 1.25 Earth radii. And then this next category is really interesting too, because this covers both the truly terrestrial things, so rocky things that could be like the Earth, and this transition region between those two peaks in the occurrence rate diagram, where you have the rocky things and the likely sub-Neptune things with maybe gaseous envelopes. And so these hundreds of planets that we expect to discover will really help us understand what's going on with planet formation in that size range. And then, 1,000 things like Neptune are a little smaller than Neptune, a small number of giant planets in the selected target stars. So these are the stars that will be observed every 2 minutes by TESS. But at the same time, TESS will return every 30 minutes an image of the entire field of view. So we will, at 30-minute cadence, observe the whole sky for 27 days at a time, or 54 days in the overlap, up to a year at a time for some objects. And from those, up to 17,000 giant planets, 3,000 sub-Neptunes, and 500 super-Earths. You notice at the same time EBs, HEBs, BEBs, eclipsing binaries, hierarchical eclipsing binaries, so triple systems, and background eclipsing binaries that are diluting the light of a brighter star. So hundreds of thousands of these pesky binary stars, which some people are really excited about, and they have their place. Yes, yawn. They have their place in history. They're wonderful for stellar astrophysics and understanding stellar evolution and stellar structure, which is important for exoplanets because then we know how big single stars are when we benchmark against binary stars. But we want to get rid of all of those. So we have our work cut out for us if we want to dig into the giant planet population. But really what we want to do is focus on the smaller number, still a large number of small planets around bright stars. This is another view from a different simulation, basically showing the same thing, distribution on the sky of where we find all these planets, concentrated near these poles, the continuous viewing zones of James Webb. And the thing I wanted to show here was that the brightness, so Kepler stars tended to peak around 14th or 15th magnitude. This is logarithmic. So things that are 10th magnitude and 9th magnitude and 8th magnitude, those things are going to be tens to hundreds of times brighter than the typical Kepler stars. And so these are going to be the ones that we're really excited about studying. At the same time, TESS will observe, one thing I didn't mention, I don't have a good graph for it, is that TESS is observing all of the nearest and brightest M-dwarf stars, which we know have lots of planets, and the habitable zones are close. So even in 27 days, you could hope to find potentially habitable small planets around those stars. At the same time, we can also expand our discovery space to hot stars. Hot stars have been avoided by surveys before because they're hard to measure the wobble of in certain ways. And TESS will do a much better job than Kepler. So effective temperature, so the temperature of the host stars, where the hottest stars are on the left. Kepler didn't find any planets around hot stars, and TESS will do a really good job of finding those. You can see the diagram filling in with red and orange points for giant planets and Neptune-sized planets around hot stars, and giant stars too. And so this is like a nice little animation that George Joe here at the CFA has created. So this is how you can confirm planets around hot, rapidly rotating stars when the measurement of the wobble doesn't work. So when the star is rotating enough, you can resolve the line profiles of the stars. They broaden. And so as a planet passes in front of the side of the star that's coming towards you, it blocks some of the light on the blue shifted side. And then as it goes across the star, it blocks light on the red shifted side. So you end up with this residual, this dimple, the shadow of the planet going across the face of the star. And it shows up in observation when the planet transits. And from that, you can determine not only that the planet's there and is real, but also what the angle is at which it crosses the star. So if it's actually in a polar orbit and going up and down, it's not going to change in velocity. It'll be a straight line going up and down this plot. And so you can learn about kind of the orientation of planetary systems and what that might mean for how they formed and evolved. So basically, TESS will be expanding our discovery space to large numbers of planets around cool stars, to hot stars, giant stars, weird systems. Now, I ran an informal survey of some folks around the hallway at one point, and I asked which TESS discoveries will be the most exciting. So this is, that you have to know what TESS will discover, and in some sense, the unknowns are the most exciting. So some people said, the primary TESS mission of finding planets around the brightest stars where you can measure the masses, get the compositions. These will be the bright things that we can observe the atmospheres of and understand the constituents in the atmosphere, whether or not they could be habitable. And I agree. I think that's really exciting. Nobody mentioned M dwarfs, actually, which is probably the second most exciting thing, but for similar reasons, because they're small stars and the signal's large and habitable zones are close. These sort of longer period giant planets, we just don't know of a lot of them because they're less likely to transit. The signals are smaller from radial velocities. And it's a puzzle kind of how the giant planets form close to the stars. I mentioned that at the beginning. It's also true of the warm Jupiters. So finding more of these will let us understand planet formation. Because TESS only observes for 27 days at a time for a lot of the sky, there will be a lot of systems that are long period, but you only see a single transit. And in fact, some simulations have been done where we expect about 1,000 single transit planets in TESS, and about 80 of them in the habitable zones of their stars. So you have to do more follow-up to determine what those what the orbits of those planets are, with radial velocities, and then ground-based follow-up with transits, sometimes space-based follow-up with transits, once you think you know the orbital period. But those will be some valuable systems because a lot of them will be in the habitable zone because of the longer period. New transiting planets and known planetary systems. So there are decades of planet searches that have gone on. So there's a lot of data in hand, and TESS will survey the whole sky. So it'll survey those systems that have already been observed. So if you already have measurements of the wobble of the radial velocities from a planetary system, or even a system where you didn't detect any planets, and then TESS sees a transit, then either you already have the detection of the mass of that transit, and so then you have the composition for free, or you already know something about the characteristics of that planetary system because you found another planet through the wobble method, and TESS finds a transiting one, or both. And so kind of like an efficient way of discovering systems and characterizing them would be to find planets in known RV systems. Young planets, so if you study young planets, then you can learn about their early stages of evolution. So in our solar system, a lot of the kind of like dynamically hot times occurred early on. So the late heavy bombardment, when most of the cratering on the moon happened, was only a few 100 million years after the system formed, maybe 600 million years or so. Or is 100 million years? A few 100 million years. Not my field, so I apologize. And so if you observe planets around that time, you can observe them before they've gone through these dynamical processes and see kind of their primordial architectures and learn about how they form that way. And then, of course, the rare events. People have mentioned ultra-short period planets that are maybe undergoing tidal decay or being ripped apart by tidal forces from interacting with a star. Binary planets or Trojan planets, right? So Jupiter has the Trojan asteroids, which orbit Jupiter in two camps, kind of leading and trailing by 60 degrees. You could have, theoretically, two planets that are co-orbital. Habitable zone co-orbital planets would be really cool. Two separately evolving species there. That'd be interesting. Alien megastructures. No, I can't say alien megastructures and go on. So I don't actually expect alien megastructures to be discovered. But in the last couple of years, there's been this Boyajian star, which Kepler discovered, which undergoes crazy dips at weird times. And people couldn't figure out a physical mechanism for it. And at one point, somebody said, well, maybe it's a Dyson sphere, an alien megastructure transiting the star. And I don't think that's actually what's going on with that system. And people are back to maybe it's dust, but we don't know exactly how. And if it's truly a rare, like a very rare system, then TESS won't find any of them. And that would tell us something. But if it's a system where it's at a certain stage of its life and there's a lot of dust from asteroid collisions or something, then TESS will find more of them because TESS will survey the whole sky. And then we can understand what's going on in those types of systems. So rare events, I think, will be really illuminating as well. So this animation is by Zach Berta Thompson, who was here as a graduate student, is now a professor at UC Boulder. And it's showing exoplanets that we knew of before TESS. So non-Kepler systems are in gray and Kepler are in blue. And this is zooming out from the solar system. So we're now 30 parsecs away, 100 light years right there. 100 parsecs, so a few hundred light years. And so there's Kepler looking in one direction and finding all of its planets mostly really far away, a kiloparsec away, so several thousand light years away. And so what we want is this number of planets, but packed in really close, because we want to be able to study them really well. And so from simulations, you can show what TESS is likely to find, predicted TESS planets, and a few around our nearest neighbors, and then you really start to fill in this local neighborhood with discovered planets by TESS. So we expect that TESS will find all of the nearest transiting planets around bright stars, and it's just, once you get out here, it's a little less impressive, but inside you saw, whoops, the sheer number of nearby TESS planets that we expect to see, which is the reason that TESS was launched, to find these that can be well studied. So, without further ado, the first TESS discovery. This is published now. We identified a transiting planet from the first month of data, actually from the first orbit. So every orbit, TESS downloads its data, and you can start processing the data. And in this particular star, we see a little dip just at the beginning, one there, one there, one there. So this is the raw data that came down from TESS after being extracted. And you can then flatten the light curve, so remove all the stellar astrophysics, the jitter I was talking about. That also shows up in photometry when the star is active. Although this is a very quiet star, the scale here is parts per million. So the transit is only a few hundred parts per million that you have to measure. The reason we're able to do so well on this star is it's a 5th magnitude star. Has a name, has a Bayer name, so it has to be a bright star. It's a naked eye star, so really exciting. It's also a star, I talked about known planetary systems and how you get a mass for free. It's a star that's known to host a giant planet in a 5.5-year orbital period, something bigger than Jupiter, where they've measured it by the wobble, but they didn't know about a transiting planet. So we see this dip. You can fold it on itself, and you see a nice-looking transit here. And because we already had the radial velocities from existing surveys, this is the radial velocity curve of the long-period planet. This is days on this axis and meters per second here. And so we're not talking centimeters per second, like I said, for the Earth and the Sun, but rather hundreds of meters per second in a longer orbital period. So this is a very massive object. 3 different telescopes had contributed data, or actually 2 telescopes, one of them with 2 different modes. And then just knowing that there is a transiting planet around this system allows us to go back to the radial velocity data and search at that period. We have a very precise period that may not have otherwise popped out because there's stellar signals that come in week-long periods or 2-week-long periods. And so it can obscure the signal of the planet. But when you look and you fold, here's the folded radial velocity curve of the outer planet. And here at the orbital period of the transit, at the transit period, is a signal that looks really messy, but the bind points in yellow actually end up giving a very precise mass for the planet. And so free mass, TESS has already discovered a small planet, I haven't mentioned the size yet, a small planet about 2 Earth radii around a really bright star, and has measured its mass already. Well, we didn't measure the mass, other people measured the mass, and we took the data. We didn't take the data, we collaborated with them on the discovery. And so here we go, we're already filling in the first month of data, we're starting to fill in this diagram. And here, there's a lot more points on this diagram than there were before, but they're kind of weighted by their error bars. The uncertain ones are really faint. And so it's one in this period, in this size range that's kind of in between the two peaks. Is it rocky? Is it more like Neptune? And you see it lies kind of close to the 100% water line. So it's not totally like the Earth. It's also hotter than the Earth, so it's not a habitable planet. But it has some hydrogen helium atmosphere. That's also interesting because that means because it's so bright and it's in this range that we're really interested in studying. This is a plot of all the known planets with their brightness, where brighter stars are lower magnitude, and the radius. And so it's among the very brightest transiting planets ever discovered. And it's in the size range that we're really interested in to determine the composition. So we can go and observe it with space-based facilities to try and figure out what's in the atmosphere. And I said it's a naked eye star. There it is on the first light image. Well, not the first light. Yeah, that's the first light image. Right there in the middle of that orange circle. So you could, on a really clear night, not from Cambridge, but from a dark sky, you could go up, well, in the southern hemisphere, you could go out and see Pi Men. Okay, so that was from the first orbit of TESS. Also in the first orbit of TESS, the first 30 days, TESS has discovered a small planet orbiting a small star. So this is LHS 3844, light and half second catalog. So half second means that it moves across the sky half an arc second, greater than half an arc second a year. So the moon is 30 arc minutes across, a half a degree across. And so this is 60 times, 1/60th of the moon. Did I do that right? No, I didn't do that right. Another factor of 60 in there. But it's moving really fast across the sky. And so that's what you get when you have small stars that are relatively bright, because that means they're nearby. And so any motion through space is going to look like a larger apparent motion across the sky. So if you see a star labeled LHS something, it's probably a small star, or at least a very nearby star. So we have the TESS data in purple and MIRF data in green. So MIRF is M-Earth is a survey that's based here, started by Dave Charbonneau, and his group runs this survey. And they look for transiting planets around M-dwarfs. And so they're a ground-based survey, so they don't observe uninterruptedly, but they observe for a long time. So you can see they've been observing this star for a while, and they actually picked it up more recently. I think they started detecting a rotation period, so they started observing it more intensely. And we actually go back and we see the MIRF data also detect this event. The orbital period is half a day. That's actually 11 hours. Every 11 hours, this planet whips around its tiny little star. And we actually got some ground-based follow-up observations with relatively small telescopes. This is an amateur who runs this, is called the El Sos Observatory. And then Las Cumbres Observatory contributed their 0.4 and 1 meter telescopes to this effort as well. You've been the ground-based data. And so we're finding the reason you can do this is because the star is so small. So that you saw in the other plot, it was 400 parts per million. This is almost 0.5% deep. And that's just because the star is so small compared to the other star. The planet is actually much smaller. It's the first planet was about 2 Earth radii, and this one is 1.3 Earth radii or so. So truly a terrestrial planet. I mentioned that it really zips across the sky, and you can see this in archival imaging. This is useful because you want to know, like I talked about how you can have a background blend of things. Well, you can rule out blends by looking at old images. That's where the star was in 1996. It was farther away in 1998, and there's TESS with its big chunky pixels, and you can't tell if there are other stars nearby. It's right there now. So you can tell there are no stars far away, or close in. This is also an interesting system because it's really close to us. It's among the closest systems. It's also an M-dwarf system, which are colored in red. And it's a small planet. You can see the radius of 1.3 Earth radii. So something, again, we can study really well. So these are kind of artists' renditions of the first TESS planets that were found. We're kind of running up at the end of the event, so I'm going to skip the last system that I wanted to show. But we can talk about it if you want in the questions. So I'll end by putting my conclusions up here. And thank you for your time, and I look forward to your questions. Thanks.
Thanks very much, Sam. So a few quick questions for Sam, and then we'll have to wrap up this. Yeah.
On the diagram of the predicted TESS discovery planets, why is it that TESS seems to have greatest aptitude for finding planets in the directions labeled June and December, or 6 and 21 hours? Because the predicted planets was definitively elongated.
Mm-hmm. So certain parts of the sky are easier to find planets. Let's see. I can't find that diagram. So basically, you have two effects. Some parts of the sky are a little more crowded as the spacecraft points, for example, toward the galactic center. You end up with a crowded field and more dilution, and you can't detect small planets as well. But also, the ecliptic poles are not, the ecliptic poles are preferentially pointed in two directions. And so those directions will end up finding more planets because you have longer time baselines in those areas, and so you can find smaller planets and longer period planets in those two directions.
What's the strangest exoplanet that you're hoping to find, and with that, what do you think the light curve would look like for that kind of exoplanet?
Ooh, that is a really good one. I think it would be really exciting to find binary planets or Trojan planets, so co-orbital in some way. I'm a little bit skeptical that you can actually have stable orbits. People have suggested you can, but it seems like it'd be really hard to form them. But then you'd end up with a transit and then a mutual transit, another transit, and one of them would be coming back across the star as it moves. So you get these weird elongated shapes with maybe a little spike in them. So lots of interesting shape transits from this.
Sam has agreed to stay on afterwards. We've got to end the live portion of this now, so I'll hand back to Sarah for a few minutes and then we can ask more questions.
So thank you all for coming tonight. Please feel free to stay and ask Sam some additional questions. We will see you back February 21st for the next observatory night. And please be careful driving home. I've received some intel the roads are a bit slippery. So happy holidays to you all. We'll see you in February.